be on the flight? Okay, that's flight 242 on the 10th. Thanks. It's pretty easy making a reservation, but how in the world did the airlines manage it all before they had computers?
In 1955, I was a reservations agent for Pan Am. That was before automation. We would have to write a reservations card in big block letters, listing all the passenger information, hopefully alphabetically. The job of the midnight crew was to correct any errors made during the day. They would go through the central file, which contained about 4,000 or 5,000 records, and re-alphabetize all of the passengers by flight and date. It was quite a voluminous job.
Since computers, reservations are a lot easier, especially when you want to make a change.
Say, for example, passengers going to Miami, and now they've decided they want to go to Los Angeles. I ask for the schedule for that particular day he wants to travel from New York to Los Angeles. I cancel the existing flight and rebook the new flight. Now, Pan Am is a major international airline, and we can store a lot of information for the passenger. For example, special meals. We have Hindu meals, kosher meals, Muslim meals, a wide variety. For this passenger, we can change his special meal request to peanut butter and jelly sandwich.
This whole reservation system is based on the idea that information, such as names, dates, and so on, can be represented inside a computer. Digital computers are most easily built from two-state or binary hardware. So any information a computer is going to use must somehow be expressed in two symbols, ones and zeros. We saw last time how numbers can be written with just ones and zeros in binary or base 2 arithmetic. But what about something like someone's name? It seems somehow more difficult than a number. How can we use ones and zeros? Well, we could assign a binary number to each name. Okay. Aaron, Abbott, Abdul, Abel, Abelard. Abelard? This doesn't seem like such a great idea. There are a lot of names in here, and there are a lot more last names than first names to worry about. And even worse, no list would be complete. Parents are always making up new names for their kids. It makes more sense to create a code to represent letters of the alphabet. Nobody except Dr. Seuss would dare to make up new letters. There are just 26 letters, and they can be relied on to spell any possible name. But how exactly can we use ones and zeros to represent letters? Well, the number of ways to do it is unlimited. I'll make one up right now. Let's call it the Garfunkel code. Each letter is represented by a string of 26 binary digits or bits. In each string, all but one of the bits have the value 0. A single bit has the value 1, and its position determines the letter. Since this is my code, I thought it would be nice to have the letters of my name up front. The letters S, O, and L are indicated by a 1 in the first, second, and third positions on the left. The rest of the letters of the alphabet can follow in order. Is the Garfunkel code the best way to do this? Well, it seems to use an awful lot of bits. Let's see if we can get away with using fewer than 26 bits per character. A single bit can be a 0 or a 1. Only two choices. So a 1-bit code can represent just 2 letters. 2-bit strings could code 4 letters. And you can figure out that at least 5 bits are needed for all 26 letters of the alphabet. 5 bits can represent up to 2 to the 5th, or 32 characters. To be able to represent upper and lowercase letters and symbols like commas and apostrophes, at least 7 bits are needed. In fact, many computers use a 7-bit code called ASCII. Now, ASCII stands for well, it's not important. Anyway, the code works like this. Each letter is represented by a particular 7-bit sequence. We can compare the Garfunkel code and ASCII in terms of efficiency. I use 26 bits for each letter, while ASCII gets away with only 7. This is bad news for my code. If a message has to be transmitted bit by bit, my code will take over 3 times as long to send. And if a message must be stored, we'd need over 3 times as much memory. There's another way to compare the two codes. Let's think of something we might want to do with text, like alphabetizing a list of words. Well, if we've used ASCII, the job is easy. Say we're only working with lowercase letters. If we consider the ASCII code of each letter as a binary number, then the numerical values of the codes are in the same order as the letters. For example, ASCII for C has the decimal value 99. The code for F has the value 102. Now, 99 is less than 102, just as C comes before F in the alphabet. So you can alphabetize just by sorting numbers. Now, using my code, alphabetizing is more difficult because the numerical values of the letters S, O, and L are out of sequence. We can't simply compare numbers anymore. We have some special cases to worry about. There's an important point in these examples of codes. There are often many possible codes for a given type of information. Which codes are good? Well, as always, we have to ask, good for what? A code is only good if it helps us do whatever job needs to be done. A code must be designed with particular uses in mind. One reason why this reservation system works so well, then, is because it's based on a good code for letters. Changing a reservation now takes milliseconds instead of minutes, and no one needs to work a midnight shift alphabetizing index cards. We've seen in this show and the last how all sorts of information can be represented in a language of 2 symbols, ones and zeros. Numbers can be represented in binary, letters in ASCII. A sound can be digitized, as on a compact disc or a synthesizer. It shouldn't come as too much of a surprise that any information can be expressed with ones and zeros. You just need to find the right code. Binary numbers can also represent images like these, which were sent back from the Voyager 1 spacecraft. But a single frame in a color image can require 6 million bits. A team of researchers at RCA in Princeton, New Jersey, is one of a growing number working to encode pictures more efficiently.
The sheer volume of data required to represent an image within a computer is a fundamental problem. However, with careful design of a representation or code, we can greatly alleviate the problems presented by this volume. Let me illustrate with an example image. Here, for instance, is a region of considerable detail within the image around the mouth. Other portions of this image contain much less detail, such as the background, which is rather uniform. A mathematician would characterize this as redundancy. We need a great deal of information to represent regions of detail, much less for regions that are fairly uniform. We've developed a code which relies on the ability to separate regions of detail from regions of redundancy.
The process begins with analog to digital conversion.
We can measure the brightness of individual points in an image using a television camera.
By zooming in, we can see these individual points called pixels or picture elements. The computer assigns a numerical value to each pixel based on its brightness, and together they're stored as a square array of numbers.
This surface is a graphical representation of the numerical values that are stored in the computer. Higher points on the surface correspond to larger numbers, which correspond to the brighter points in the image.
Converting the picture to numbers is part of most imaging systems. An important part of the RCA technique is to create a series of progressively blurrier images, each with less detail. The detail of the original image corresponds to the roughness of the surface in this graph. The blurring is achieved by a mathematical operation on the pixel values called digital filtering, and as detail is lost, the surface seems to erode. What the graph shows us is how filtering causes the numerical value or brightness of pixels to change as we move through the series of blurred images. The change in value is large for detailed areas of the image and close to 0 for uniform regions. You can quantify the change by subtracting corresponding pixel values from one blurred image to the next. So now, if we subtract adjacent blurred images, we get a new series called difference images. In these new images, large values correspond to detailed regions, small values to uniform areas. Since images tend to have many uniform regions, most pixels in these difference images have values near zero, shown here as medium gray.
The result of this is the sequence of images that you see here, where the first image shows the fine detail, the next image shows somewhat coarser detail, and each image after that shows a coarser and coarser level of detail.
Because coarse images contain less information, they can be reduced in size and represented in the computer as a smaller array of numbers. The less detail in the image, the greater the reduction. Taken together, this series is called the Laplacian pyramid, after the French mathematician Laplace.
This actually ends up giving you a complete representation of the image. That is, you can take the information shown here and run it backwards and recreate the original image that you started with.
Counting up all those difference images, we actually have a total of 33% more pixels than we started with. We seem to be going in the wrong direction. How can this process result in an efficient code for pictures? Well, subtracting images causes uniform regions in the original to become regions of zeros in the difference images. In fact, 0 is the predominant value in these images. And here's where the really clever coding idea comes in. The RCA researchers created a compact new code that abbreviates whole blocks of zeros with just a few symbols. So just how efficient is this new code for pictures?
The original image is shown on the left. The image that was coded using the Laplacian pyramid is shown on the right. The image on the left takes about 500,000 bits to code. The one on the right takes only about 65,000 bits. So that's an 8-fold savings in the amount of information to be stored.
In the near future, we see applications of these techniques in a number of areas. In image storage, for example, of medical images, an electronic encyclopedia, robotic vision, where we would provide a robot with vision to find parts on a conveyor belt and assemble components, and in image transmission over telephone lines, for example, with applications to home shopping.
And if it happens to be a home you're shopping for, you could call up images on your personal computer. But it takes about 1.5 minutes to send a single image by telephone if you transmit it line by line like a TV picture. Using the pyramid representation, it only takes 12 seconds. And after just a second or two, you'll have a pretty good idea of what you're looking at, in case you want to move on to the next choice. That's because the coarse features are transmitted first and the details are filled in later. At RCA, researchers are working to reduce the redundancy in graphic images. But redundancy isn't always bad. In fact, there are times when it's critical. Duplication is built into modern aircraft, from mechanical controls to computer systems. Even the crew of the Swiss Air jet is trained to back up one another's performance. Co-pilot René Haueter explains the backup systems in the Boeing 747.
To start with the technical systems, we have 4 electrical systems, we have 4 hydraulic systems, we have 4 pneumatic systems, and all these systems power a certain equipment, and if one of these systems fail, it actually doesn't matter much.
Sometimes during a final approach, the crew relies completely on 3 computerized autopilots.
We need all the 3 autopilots to control the aircraft. For this automatic landing, in case something goes wrong, we have to have this backup or redundancy.
Having more than one computer is good protection against a catastrophic failure, like overheating or a power outage. But there's another kind of problem that can be corrected by a different type of redundancy. Errors can occur within computers when a particle of radiation strikes a memory cell. These particles can come from small amounts of radioactive elements, uranium and thorium, that are found in the ceramic packaging of memory chips. So what can be done about these occasional random errors? Richard Hamming, a mathematician at Bell Labs, came up with a very efficient solution in 1948. The answer lies in choosing the right representation for information, a redundant one that will allow errors to be detected and corrected. Suppose we want to represent 4 bits in memory in such a way that we can correct any single error. Here are the 4 bits that we want to save. Arranging them this way lets us think about the problem more easily. Let's now draw 3 circles to make what's called a Venn diagram. There are now 3 empty spaces in the diagram. Let's fill them in with a 1 or a 0 so that each circle contains an even number of 1s. We can think of these 7 bits as a representation, a redundant one, of the central 4 bits that we want to preserve in memory. The 7 bits are called an error-correcting code. Here's why. We can fix any single mistake by using a simple algorithm. It works like this. Suppose that there's an error in one of the bits. Let's count up the number of 1s in each of the 3 circles. 2, 2, and 3. 2 of them have an even number of 1s. I'll call circles like this good, but 1 circle has an odd number. I'll call this bad. We can tell there's an error somewhere in the diagram because there's a bad circle. So far, we've detected an error. Now let's see about correcting it. Since the Hamming code is designed to handle 1-bit errors, let's try to make all the circles good by changing the value of just 1 bit. Obviously, changing any of the bits outside the bad circle isn't going to help. That leaves 4 bits to think about. If we change this bit, well, we've made this circle good, but now we've made this circle bad. And the same thing is going to be true for this bit down here. If we flip the middle bit, things get a lot worse. We fix the bad circle, but ruin both good circles. There's only 1 bit left to try. Sure enough, when we change it, all the circles are good. So that's why the Hamming code works. For any single error, there's just one way to fix it, the correct way. And because the Hamming code is an efficient way to fix errors, it or a similar code is built into the memories of many modern computers. Suppose, for example, you have a smallish computer that can store about 8 million bits. If you take your chances and don't bother with error correction, there'll be, on average, a mistake due to radiation about every 43 days. That's almost once a month. But if the computer uses Hamming's error-correcting code, the rate of mistakes drops to 1 every 63 years. Now, this Hamming code is only designed to handle 1-bit errors. More sophisticated codes can correct bigger errors that might appear to be hopeless. One of these is used for audio recordings on a compact disc. A tiny flaw on a disc can affect a large number of bits. Therefore, a code is used that can correct up to 4,000 consecutive errors. That's enough error correction to cover most kinds of damage. Satellite dishes, the new standard for transmitting television pictures with the highest quality and lowest cost. Anyone with a few $1,000s to spare can climb aboard this technological bandwagon. And until recently, backyard dish owners could use their new toys to intercept transmissions from national programming services to local cable television systems. Home Box Office is the largest of these premium services, program channels for which the cable viewer is supposed to pay a monthly fee. Paul Heimbach is a vice president at HBO.
Home Box Office provides 2 premium pay services to cable operators, HBO and Cinemax. These 2 services originate here in this facility in Long Island, New York. They're transmitted or uplinked to domestic satellites where they're redistributed to our cable affiliates across the United States. HBO started using satellite distribution in 1975. In 1980, we began to see an increase in the number of unauthorized users receiving the HBO signal from these satellites. And in 1984, it's generally accepted that there were perhaps 1 million backyard or unauthorized dishes in operation. In 1980, as we saw the number of those backyard dishes increase, we felt that it was necessary to somehow secure or scramble the HBO signal to prevent unauthorized reception of our programming. The video is scrambled by making the picture into a negative. That is, lights become dark and darks become light. In addition, timing information in the video signal that's used by home TV sets to position the picture on the screen is also removed. The audio signal is digitized, much like a compact audio disc, and encrypted. Authorized users receive a monthly key to activate their descramblers. Without that monthly key or password, the signal is totally unintelligible.
HBO has to get the password out to 7,000 local cable television operators like this one all around the country. Now, the only practical way to deliver the password every month to all those paying customers is to send it by satellite, right along with the scrambled signal. But then it's also going to be received by all those unauthorized backyard dish owners. So HBO's problem is to protect the secrecy of the password. HBO's solution is to disguise the password by altering the way it's represented, using a code. The technical term for the process is encryption. So it might seem that all HBO needs to do is transmit not the password itself, but an encrypted version, what's called a cipher. Then local cable companies can decrypt the cipher and recover the password and the TV signal. In fact, HBO takes an extra precaution. The password is encrypted individually for each subscriber. HBO transmits a stream of ciphers, but each local company can only decode the one intended for it. If a local operator fails to pay its bills, HBO can cut off service by not transmitting that operator's individually coded password. Let's see just how it's encrypted. At the heart of the process is an algorithm called a pseudo-random generator. This algorithm outputs a pseudo-random sequence of binary digits which appears random. However, it's crucial that the pseudo-random number be produced by a definite procedure because it must be repeated when we decrypt the password. Next, the pseudo-random sequence is combined with the password, bit by bit, like a zipper, to produce a cipher, or disguised form of the password. Remember, it's the cipher and not the password that's sent out by satellite along with the scrambled TV signal. Let's take a closer look at how the password is combined with the pseudo-random sequence. If the two numbers are the same, they're combined to make a 0. And if they're different, they're combined to make a 1. Notice that the cipher alone contains no information whatsoever about the original password. For example, a 0 in the cipher has a 50% chance of standing for a 0 in the password, and a 50% chance of standing for a 1. So even though the would-be satellite pirate can intercept the cipher, he can't deduce the password from it. Authorized subscribers like this cable system also receive the encrypted password from HBO via satellite. But the cable operator owns a decoder box that enables it to decrypt the cipher. Thanks to the elegance of the binary representation, decrypting is identical to encrypting, just performed in reverse. Inside this box, there's a copy of the pseudo-random generator, and it produces the same sequence that it did for encryption at HBO. This sequence is then combined with the cipher to produce the message, the password. It might come as a surprise that the pseudo-random number algorithm is public. You can get a copy from the National Bureau of Standards for a self-addressed stamped envelope. So where's the security? It lies in the structure of the algorithm. The algorithm must be given a long binary number called a seed before it's run. For each seed, the algorithm will produce a different pseudo-random sequence. A cipher can only be decrypted by using the identical seed that was used for encryption. Now, each local cable operator's descrambler box has its unique seed built into it. And to thwart thieves, the box is engineered so that there's no way to uncover the seed by tampering with the box. Say you're still not convinced. You've got the algorithm and some kind of decoder box. You could try to beat the system by trying to guess the seed of one of the subscribers. But the seed, like the password, is a 56-bit binary number, so you might just as well try to guess the password directly. If you test all possible 56-bit numbers, one of them is bound to work. This approach is called an exhaustive, or more appropriately, an exhausting search. How long would it take? Well, suppose that passwords were only 4-bit numbers instead of 56. Then there would only be 2 to the 4th, or 16 possibilities to try. One of these passwords will be the one that unscrambles the TV signal. That was pretty easy. But how long would it take to guess a 56-bit password? Well, there are 2 to the 56th possible passwords. That's more than the number of stars in 100,000 galaxies the size of the Milky Way. If you tried 1,000,000 passwords per second, it would take you on the average over 1,000 years to hit on the correct one. By the time you find it, that show you wanted to watch will probably be over. We've looked at how many different kinds of information can be represented in the binary language of computers. And we've emphasized that any particular type of information can be encoded in more than one way. Choosing a code wisely entails analyzing your needs and exploring the mathematical possibilities. For example, when the goal is fast and flexible text processing, ASCII is a good choice. For encoding images in a compact and efficient way, new methods like the Laplacian pyramid are being developed. To detect and correct errors, a good code will use redundancy wisely. And to protect proprietary information, a binary code can be encrypted. To choose the best code for a particular application, you have to analyze different possibilities, and mathematics is always at the heart of this kind of analysis.